In this video, we're going to practice some graphing fundamentals by looking specifically at displacement graphs. Before we can get into graphing, let's first define what motion is. Motion is defined as an object's change in position relative to some reference point. This astronaut, relative to the Earth, is moving at 17,000 miles per hour, but relative to the shuttle, not moving at all. So every time we are talking about motion, we have to define some reference. Usually we will define the surface of the Earth as our reference, not the Earth orbiting the sun or the sun moving in the galaxy. We use something that kind of matches our reference point. Now, distance and displacement, two terms that sound very similar. Distance is known as basically how far you have traveled. Displacement is similar, but it's how far you are from where you started, how far from the origin. The easiest way to think of this is to see a couple examples. An example of distance is this blue line. If I wanted to travel from Minnetonka to Niagara Falls, I would have to follow the roads. I couldn't drive in a straight line. But where I am from how far from the origin, I can measure that from it as a straight line and just basically draw a line from where I ended to where I began. In a one-dimensional example, let's look at this scenario where you walk 5 kilometers east, you turn around and you walk 2 kilometers west, you turn around again and walk another 4 kilometers east. Your distance is basically how much you have traveled. Like if you had an odometer that was tracking your distance, you've gone to 5 plus 2 plus 4 for a total of 11 kilometers. Your displacement doesn't care about the middle part. It's just comparing where you ended to where you started. So you're looking like this. Your total displacement is 7 kilometers. You started at 0, you ended at 7. It didn't matter that you turned back around. Now we can plot this on a position versus time graph or a displacement versus time graph. In our situation, they're going to mean essentially the same thing. Now we don't know exactly what the time scale is. So we're going to say over a certain period of time, you went from 0 to 5. Over a certain period of time, you went from 5 back down to 3. In a certain period of time, you went from 3 to 7. This is an example of a displacement graph showing that one-dimensional motion going back and forth. Displacement is different than distance because displacement, you can go backwards essentially, and that number can get smaller again. A stroboscopic photograph is another way that we can talk about motion. In this photograph, we see this ball moving, and the way that we see it moving is a camera took a picture of it every 0.04 seconds. So think of a strobe light, and you can see that ball making its motion. Now, if it travels farther in that same duration of time, it means it's moving faster. So here, where it's moving the fastest is down at the bottom, and moving the slowest is here up at the top. And we'll see that when we talk about free fall and projectile motion. Now, we can also see different types of motion using this type of photography. A constant velocity would look something like this billiard ball moving around, where it's a very even incremental spacing. Whereas accelerating motion is looking like this free fall, where it starts off moving pretty slow and then spreads out and it goes down. So if we look at the spacing between the pictures, we know that more spacing equals moving faster. It's covered more ground in that same time interval. We're going to use that idea and then look at different types of motion. Now, motion, you need more than one measurement. If I had these three carts and I said cart A is at 0, cart B is at 2, and cart C is at 3, and I said which one's going to win? Well, you say maybe C because it's closer, but that doesn't tell you anything about its motion. Even if I told you 1 second later they're all tied at the 4 meter mark, now you know something about motion. Cart A traveled 4 meters in that second, but cart C only traveled 1 meter. So now your answer might change just a little bit. 2 seconds, it's maybe changed again. At 3 seconds, now we have a little bit more information about this motion. With these numbers alone, you could probably piece it out, but putting them on a graph is the best way to do it. I graphed this. Part A, we can see it started off moving quite a bit, but every second started moving a little bit less distance. Cart B was very constant the entire time. It moved 2 meters every second. And cart C started off kind of slow, but then picked up speed as it went. So each of these carts had a very different journey. And that graph really shows that journey. So let's look and define some of those different types of motion and what that looks like in a displacement graph. Let an object not moving. Let's place it here and position mark 4. And we look at it over time, it's always at the 4. It's a pretty boring motion. It's not moving at all. So our displacement graph basically says at any time, my displacement is 4. Its position is 4. Okay, if I set something in motion, let's say it's moving forward, here it's a little bit more interesting. At every time interval, it has moved exactly 1 meter. So my stroboscopic photograph looks like this, and my graph looks like this. It's a very constant motion moving forward, starting at 0 and going up. If I have an object moving backward, say it starts at the 7 and it moves down, oh, it's going to look very similar, but now it has a downward slope. So we can use this idea to show velocity. If I have two objects in a race and I see obviously the green was moving faster, if I track the motion in the same way that we did, this red one looks exactly like it did before. It moves 1 meter every second, and we see its motion like this. The green one, however, every second, it actually advances 2 meters, so its graph is going to look something like this. We can see that the slope has something to do with the velocity. The steeper it is, the faster it is moving. So let's take that idea and speed something up. Let's change its velocity. So I have an object here that starts at 0, and then we track its motion. It starts off not moving very fast, but every progressive second, it travels a farther distance. And what it looks like in our graph, if we are advancing the same time interval, is it starts to curve. It curves upward. Slope gets steeper, showing that it's getting faster. If I show speeding up, moving negative, it's the same general motion. It starts close together and gets farther and farther as the time advances. But now, since it's moving negative, it is going down and getting steeper that way. So we see that curve. Both of these curves are showing that speeding up motion. So if I said, here you got two graphs, and I asked you to describe it to my 5-year-old, how are these similar? Well, they're both curved, but they're also both speeding up. How would I know they're speeding up? In this case, we know that they're getting faster because the graph is getting steeper. One is getting steeper in the positive direction, one is getting steeper in the negative direction, but they are both steeper, and steepness corresponds to speed, how fast it's moving. All right, let's look at what it might look like then slowing down. If it's slowing down, it means it starts off pretty steep. It starts off with great spacing, but then that spacing gets smaller and smaller until it basically levels off. Slowing down is going to look something like this. Slowing down in the negative direction. This is kind of weird to see. Normally, we don't see something slowing down, going down. So think of like an elevator coming down or a yo-yo coming down to its lowest position. It starts off moving fast, and then it slows down as it gets to the 0. So we see that graph making a curve leveling off this way. So again, we can see that the slope matters in talking about how fast or slow something is. If I gave you these 4 graphs, these are all accelerating or changing velocity. Which graphs represent an object that is moving in the negative direction? Well, we're looking for a graph that starts at a positive or a more positive displacement and then getting closer and closer to 0 or going down. In that case, that would be both B goes down and C goes down. If I asked which graphs represent an object that is slowing down, now we're looking at slope. Speeding up was getting steeper, slowing down is leveling off. So both A and C are examples of an object that is slowing down. All right, that was a quick overview, but our main takeaway is you should be able to describe the difference between distance and displacement, why those words sound similar but are describing different things. You should be able to calculate the distance and displacement for an object in 1D motion. Think that object that went back and forth, you're able to see its distance versus displacement. You should be able to plot constant velocity and displacement time, also changing velocity and displacement time, and then use the displacement time graph to identify if something's moving positive or negative, or if it's speeding up or slowing down.